Welcome to Unit 4, Lesson 4B. This lesson is actually making use of what we learned about in Lesson 4. So we're going to be talking a lot about bonding and molecular geometry. Now, before we go on to what we have to do for today, I just want to mention a few of the things that we've talked about so far. So we have already covered metallic bonding and ionic bonding, and we are currently in the midst of talking about covalent bonding. So far, we've learned how to write Lewis structures, how to count valence electrons, how to calculate formal charge, and when molecules have resonance. What we're going to add on to that, and what we talked about recently, was VSEPR theory. We differentiated between electron domains and bonding domains. We talked about shared and then unshared electron pairs, and we went over all the bond angles using those models, those awesome 3D models that we saw in our earlier lesson. What we still have to do before the end of this unit is to finish talking about covalent bonding, and that's going to include a discussion of sigma and pi bonds, which we're going to talk about today, a discussion of hybridization, bond and molecule polarity, molecule symmetry, and then intermolecular forces of attraction, which we'll talk about next week. And those include London dispersion forces, dipole-dipole forces, hydrogen bonding, ion-dipole interactions, and network covalent bonding. So, if we look at the one topic that we're going to add to what we learned, it's called sigma and pi bonds, and it's a very simple topic. It's just differentiating between single bonds, double bonds, and triple bonds. So if we have a single bond, which is what we're going to encounter most often, that bond is called a sigma bond and occurs along the bond axis, the imaginary line that connects the nuclei of two atoms. If we have a double bond, we actually have a bond along the axis, the bond axis, and then we have a second bond called a pi bond, which takes place above and below the axis or in front of and behind the axis. And we'll draw pictures to show what that looks like. And finally, a triple bond, which consists of one sigma bond, again, along the bond axis, and then two pi bonds. So we'll have one above and below, we'll have one in front of and in back of the bond axis. So as it says in the slide here, sigma bonds refer to the bonds that occur along the bond axis, the straight line that exists between the nuclei of two bonding atoms, and pi bonds refer to the overlap of unshared p orbitals. So we're going to differentiate those for those of you in accelerated honors, and those occur above and below or in front of and behind the bond axis. Okay, so on this slide, this is an example of what we're going to work on today on bonding and molecular geometry. So if you notice, the columns that I've highlighted in green provide the information, so you don't have to do anything there. That's information about the molecule. What we're going to work on today is going through all of these yellow columns, and we're going to hold off. So these columns that are down here at the bottom, we're just going to wait on. We're not actually going to submit the assignment at the end of the week this week. Instead, what we're going to do is hold off, and then next week when we talk about intermolecular forces of attraction, we're going to complete the information that's in this bottom. So I'm going to start off by talking about the number of valence electrons. So there's the way that you're supposed to do this, which is to identify the number of electrons based on the group on the periodic table that the element's in. So hydrogen, which is in group 1, would have 1 valence electron. And then oxygen, which is in group 16 on the periodic table, would have 6 valence electrons. So you'd say, okay, I have 1 oxygen and 2 hydrogens, so that's 6 plus 1 plus 1, or a total of 8 valence electrons. However, because of the way that I've had to modify this assignment for cyber and for remote learning, you could also just, full disclosure, count up the number of electrons that are here. Okay, so the next thing that you want to do is double click on the box for the drawing, and you're going to make your Lewis structure next. So we're going to start by moving all of our atoms into kind of a workspace down here, a little bit lower. And remember that hydrogen will never go into the center of a molecule because it is only capable of making 1 bond. So then the next thing that you want to do is connect up your outside atoms. This is just like we learned in Lewis structures. Connect up your outside atoms to your central atom. And again, you could grab these in pairs of 2. That makes it moving them around a little bit easier. And lastly, what you want to do is take any extra, because remember, you can't have more than 2 on hydrogen. So you take any extra and you put them on the central atom. So we are going to do that right here. So when you're all done, you should have a drawing that looks like this. I'm just going to move my hydrogens in a little closer. And you can also, it's up to you, just select the entire thing and just move it up to the top left corner here. That seems to take up less space on your sheet. There we go. So we have our Lewis structure. Now, in terms of formal charge, those of you in accelerated honors who need to include formal charge on these, the formal charge for hydrogen is going to be 0 when it makes one bond. So we're going to put in a 0 here next to the hydrogen. And the formal charge for any oxygen atom that is making 2 bonds and has 4 electrons to itself would also be 0. So it'll be 6 valence electrons minus 2 bonds minus 4 electrons that are unshared. So all of our formal charges in this example will be 0. So I'm just going to copy this. Again, this is for accelerated honors. Copy this 2 more times and just place these zeros at all 3 positions here. Okay, so if we look at the next part, and this is for everyone again, what we want to do is count up the number of electron domains or areas around the central atom where electrons are found. Remember, we only do this around the central atom, so we're not doing this for any of our outside atoms. So around the central atom, we have 1, 2, 3, 4 electron domains, 2 of which are bonding domains. So if you look up on your VSEPR theory guide that we worked on earlier this week, it says electron domain geometry name. This is going to be tetrahedral because of the 4 electron domains. And the molecular geometry name is going to be bent because we have a 4-2 combination. So the next thing that we're going to do is make our molecular geometry picture. Again, we're going to kind of pull this into a clean workspace over here on the side. Remember that we have tetrahedral shapes. We're going to have one up. We're going to have one down and to the left. We're going to have one that's coming out of the plane of the board and one that is going back behind the plane of the board. And we could put our 2 hydrogens, really we could put them anywhere, but being consistent with our VSEPR theory guide, we're going to place them on the position pointing toward the back and the one pointing toward the front. We're going to put our pairs of electrons just where we have them on the VSEPR theory guide. So one on the top and one down here to the left. Okay, and then the last thing that I'm asking you to do, and we'll make use of this next week, is to take these 2 arrows that are here, and we're going to position the arrows so that they point toward the more electronegative atom in each bond. So in the case of our first bond between oxygen and hydrogen, again, it doesn't have to be perfect, but we're going to try and place them along the same line that we have for the bond itself. So we're going to place the arrow so that it points toward the more electronegative element. So the more electronegative element in this case between hydrogen and oxygen is the oxygen. So we're going to make sure that we place the arrow so that it points toward the oxygen in both places. And once you're doing that, once you're done with that, you can save your drawing and it will place your drawing right in here. You could also change the size in here. Okay, last part. So completing these 3 columns. So for the bond angles, remember for a 4-2 tetrahedral bent, we have a bond angle of 104.5 degrees. So 104.5 degrees, and we have just one of them because we only have 3 atoms. We have 2 sigma bonds. Both of these are sigma bonds, no double bonds. So we have no pi bonds in this example. So this represents a completed example problem here. What I'm asking you to do, if you are ready for this, go ahead and complete the next. So I believe there's, depending on what level course you're in, there's somewhere between 6 and 12 more example problems. So what I'm asking you to do is to finish those, and I will take a look at your work, your progress on those throughout the week, but please do not submit this assignment. If you accidentally submit it, that's fine, I'll just unsubmit it for you. But we're actually gonna finish the rest of the assignment, these 4 columns at the bottom, next week. All right, if you have any questions, please reach out. Many of you have been doing that. I think it's been helping a lot. And I'll see everyone. Have a great week.